So if I could just bring up the first slide there. So what we know from a lot of studies in ecology is that phosphorus is often limiting to the growth of all kinds of organisms, bacteria, algae, higher plants, even higher animals themselves. And this picture from the Tennessee Valley Authority shows quite clearly that phosphate added on the right-hand side of the picture is limiting also to crop plants. And so we add a lot of phosphorus in fertilizer, and in fact, phosphorus-based fertilizers are one of the pillars of the green revolution. So phosphorus is limiting in a lot of different ecosystems, and it's limiting for the reasons that Felisa described, because life as we know it, organisms that we know around us, rely on phosphorus to build nucleic acids and other molecules that they need to grow and proliferate. So phosphorus is well known to be extremely important for all kinds of organisms and ecological systems. So if we're going on to the next one, because phosphorus is limiting and everything needs it, it often turns out also that when phosphorus leaks out of systems, like out of agricultural fields or out of cities or such, it functions as a pollutant. And here you can see a lake on the bottom half has received phosphorus. The top side has only received carbon and nitrogen. The bottom side has received carbon, nitrogen, and phosphorus. So phosphorus is necessary to have massive algal blooms that lead to the greening of lakes like this and eutrophication. So phosphorus is a big issue for sustainability and the quality of aquatic ecosystems. So we know that phosphorus, because it's limiting, because it's so important to organisms, often functions as a pollutant when it leaves human hands. Now, if we go on to the next slide, we can also start to talk about, well, where does this phosphorus come from that we use in fertilizer? Well, it comes from just a few places around Earth. It comes from mines of phosphorite deposits that were built up over tens of and hundreds of millions of years by biological processes. These mines are located in just a few countries around the world. The United States has phosphorus reserves in Florida and North Carolina that are rapidly being depleted because of fertilizer consumption. Morocco has major phosphorus reserves, as does China, but the distribution of this resource is relatively scarce around our planet. And so because of this scarcity and its geographic distribution, and because of the burgeoning demand for phosphorus fertilizer, there's some concern, and we can see the next slide, please, among scientists that supplies of phosphorus that support the green revolution and high agricultural production might become scarce, at least supplies of cheap phosphorus. And so we need to get a lot cleverer about phosphorus in society, and it's really exciting to think about the possibilities that are raised by a clever organism that has evolved a way to do without phosphorus, possibly, as we're talking about today. So if we go on to the next slide. So as I think about the ramifications for the possibility of an organism that doesn't use phosphorus, the possibilities start to run away to think about how it might be used in wastewater treatment, how it might be used in recovering phosphorus from various sources, how it might be used in bioenergy production, and other sorts of possibilities. So really, we have a new way of thinking now, if this study holds up, that there are organisms that are possibly able to grow without phosphorus. And as someone who's studied phosphorus for my entire career, essentially, and who regularly gives lectures about phosphorus in which I state that every living thing uses phosphorus to build its DNA, the idea that I'm sitting here today discussing the possibility that that's not true is quite shocking. So, Felisa, I have to thank you and blame you for making our lives somewhat more difficult. So it really is quite a remarkable report in the context of what we know about phosphorus and its importance in ecosystems.
So thank you, Jim. It sounds to me like you're going to need to go out and find a new textbook to teach all those students about what elements are used to build life.
Well, I don't know about a whole new textbook, but certainly some paragraphs and sentences are going to have to be rewritten as of today.
Give me some time, Jim. I'm at the beginning of my career, so see you on the back end of that.
Okay, Felice, I'll be happy to review it. I'll get started.
Great. Thank you, Jim. Our next speaker is Dr. Stephen Benner, from the founder and distinguished fellow from the Foundation of Applied Molecular Evolution. And he's spent a lot of his life as an organic chemist and studying the chemistry of life. What are your thoughts?
Well, I'm the curmudgeon here. I'm the chemist who has been brought in, as Felisa knows, to throw wet blankets on things and to try to damp a little bit the enthusiasm. My next 3 minutes will be successful if I convey to you folks why chemists think that this is an exceptional result, and why, therefore, chemists will, like Carl Sagan says, require exceptional evidence to support it. And I also want to make sure you folks understand why we nonetheless find it interesting. What Felisa has found, of course, is a microbe that grows in the environment which has a lot of arsenic and very little phosphorus. The Astrobiology Institute, which we are parts of, is the one place in American science where you can go to find geologists and microbiologists and astronomers and chemists together, where we can have the productive clash that leads to big discoveries about big questions. What is life? What could alien life look like? And so my goal in the next 30 seconds or so is to try to give you, as a layman, the understanding of how this is an exceptional result, how it might be looked at in greater detail, because one thing that will survive is the Felice's microbe, and that will be an excellent system to explore questions about how arsenic is tolerated and phosphorus is limited in organisms that are placed under environmental stress. So I brought my Richard Feynman props with me, which is a representation of a molecule, right? And these molecules are, say, representing a biopolymer, and of course we're making them out of steel, and the result is that it's tough, right? And of course, as Felisa has mentioned, arsenate is made out of, in this particular case, aluminum foil. And of course, it's not as tough as steel, but when a bacteria is going to try to form a new chain, it's going to try to find in the environment the links that go to form the chain. And of course, if there's arsenate around, as a weak link, it will maybe confused and maybe deceived by the structure of arsenate and the similarities to join two chains together, not by a steel chain, but rather by an arsenate chain. And of course, these are compounds that have been studied in model form. The specific arsenate DNA has actually never been isolated, but there are compounds that are similar to it. Different kinds of atoms, but still carbon, oxygen, arsenic, oxygen, carbon linkages. And so we know that they're relatively unstable. They fall apart with half-lives measured in the order of minutes, conveniently. And so when you try to put them into a DNA molecule, right, and then you put it under stress, they fall apart. And then, of course, your biological system says, oh, my God, I've just destroyed my molecule. I've got to go back again. So, again, if there's arsenate in the environment, right, you can get the story. You waste a lot of energy and a lot of time trying to put into DNA backbone arsenate, where if the arsenate ester falls apart, you're effectively saying that arsenate is the, I guess we call it the wolf, demon wolf, or demon sheep in sheep's clothing. It fools the enzymes into taking it instead of what it should take. There are two ways that biological systems in general can manage this. One way, of course, is to get very good at distinguishing between sheep and wolves in sheep's clothing, and therefore the end result is, of course, that you don't get fooled by the analog. The other possibility, it's also conceivable that the biological system can have evolved to manage the weak link. And they might manage the weak link by, for example, binding something to the weak link, sequestering it, keeping it tight. But the difficulty that we're having, or in fact almost anybody with chemistry who is familiar with this literature will say is, well, wait a minute, this DNA molecule has allegedly been isolated away from the other molecules in the biological system. So we remember all this old chemistry, and we don't believe it. And that's what you're going to see a lot of people saying. Now, keep in mind, old chemistry can be wrong. And in fact, one of the wonderful things about being in a science is, as Richard Feynman would say, science begins when you distrust experts. And of course, as the expert in chemistry, I'm saying that you should distrust me. But the bottom line out of all this is that what you're looking at here is an exceptional claim based on the context of the chemistry. And of course, when we can go into great details about what experiments you might do in the future to explore this, but what Felisa has produced is a very, very useful system to go ask these kind of questions. One last point. Remember, the weakness of the link is a weakness measured at room temperature, 35, 37 degrees centigrade, 98.6 degrees Fahrenheit, in water. If you go to an exotic environment, and the National Academy of Sciences produced a book, which is actually you can go have. It's coming out of the National Research Council, called "The Limits of Life in Limits of Organic Life in Planetary Systems." You realize that in our solar system there are places, Titan, a moon of Saturn is one of them, where the temperature is much lower, where very reactive species like arsenate could very well be useful because although they're too unstable to exist in many environments on Earth, they're not too unstable to exist in an environment like Titan, which is at minus 290 degrees Fahrenheit. So it's a cold environment. And in fact, you might very well want to have the increased reactivity of arsenate in that environment just to get the reactions that you want to make your biopolymer chains go a little bit faster. So again, my role as the curmudgeon is to say, this is an exceptional result. I hope I can convey to you a little bit, maybe not in technical language, but in graphic language, why the chemist views this as an exceptional result. And so you will understand why in the NASA astrobiology program over the years, as these various disciplines of chemists and who are the doubters or the deniers, the microbiologists, the geologists will interact in a way to bring forward the process that science is, which is, of course, the clash of contradicting cultures in an effort to come up with the truth, to inspire, of course, Americans' youth to go through the effort of studying science, so they knowing full well that there are these kinds of very interesting questions out there, like what is life and where might we find it, if not on Earth.
Thank you, Steve. I have a question for you. So, would you, as an organic chemist, consider replacing your graduate students with microbes to explore these reactions?
Many of my graduate students are undoubtedly watching, and I love you all, and I wouldn't think of replacing them.
Okay, fair enough answer. Okay, our next speaker is Dr. Pan Conrad. She's a planetary scientist at the Goddard Space Flight Center and also the deputy PI in an investigation that will be flown on the Mars Science Laboratory to be launched in a year from now. It's the first astrobiology mission since Viking, and whose goal is to look for evidence of habitability and the potential for current and past life on Mars. Please, Pan.
Well, I don't think I'm going to classify myself either as curmudgeon or otherwise.